Hi guys, so this quick video is just going to be about something called the intermediate value theorem. And if you remember, we've been talking about functions that are continuous, and we defined continuity and we talked about continuity at a point and a continuous function. And many of you have realized by now that this definition of a continuous function is kind of confusing, because actually a continuous function can have a discontinuity. And so the intermediate value theorem is one of the reasons that continuous functions are so important, and it's kind of like one of the reasons it's worth all the trouble it takes to prove that a function is continuous. Here's the theorem as it's presented in your textbook. Take a moment to copy it down. If you can't see it because this filming is blurry, it's on page 83. And once you've written it down, let me talk about the meaning. Great, so basically the idea is if you have a continuous function and you know 2 points, like a starting point and an ending point that happen somewhere on this function, the intermediate value theorem says that even if you don't exactly know what happens in between these 2 points, if the function is continuous, that's the premise, that's what you check, then you automatically know that the y values of these 2 points and every y value in between gets hit by the function. Another way to put that might be, if you know that this function has a y value of 1 at some x value and 2 at another x value, automatically guaranteed there has to be at least 1 point somewhere in here that hits 2.5, and at least 1 point in here that hits 2.7. etc., etc., etc. Every function gets hit. Let me give you an analogy. When we travel, here's a map of the world. Suppose I tell you that I'm going to travel from the United States to India to visit my family in December. Well, you don't necessarily know how I'm going to go. Obviously, I'll probably take a plane. It could go this way, or my plane could travel like this, or my plane could travel like this, or actually my plane could even travel the other way around the world. You don't know the path I'm going to take, but you know that if I start in the United States and I end in India, I have to cross a date line somehow, either on this side of the world or on the other side. It's guaranteed that I'm going to cross that value, even though you don't necessarily know when or how. The other analogy from class was the teleportation. If people could actually teleport, then we would not be a continuous function, and you couldn't guarantee that I was going to fly over the ocean. But in the real world, you can't teleport. So if you get from here to some other place, it means that you automatically have to pass through a bunch of points in between. That's all the intermediate value theorem is really saying. So here's how we use it. It's just one example, and then we're going to do a bunch just like it. If you haven't already written down the idea behind the intermediate value theorem, please pause the video and summarize for yourself in the side of the notes. The idea is much more important than the actual theorem. Okay, here's your example. We're going to solve this problem, and the question is a very simple sounding question. It just says, is any real number exactly 1 less than its cube? Seems simple. Let's see what it looks like. So we haven't done a lot of word problems yet in calculus, but you should remember from Algebra 2 that in order to set it up, this is a simple way to set up a word problem. What are we looking for? Well, we want to find a number. I'm going to call this number n. And not just any number, but we want an n such that a particular thing happens. In other words, we want to find some number that satisfied a particular condition. And I'm going to try and translate those words into a condition that's written in a mathematical statement. Well, what does it mean for a number to be exactly 1 less than its cubed? Well, I know that the cube of the number would be like n cubed. And the actual number is n. So if n is exactly 1 less than n cubed, that means that if I subtract them, n cubed minus n, I should get an answer of exactly 1. Make sense? So looking at this, we want to know whether we can solve this equation.
Is this what you're waiting for?
And here's what the work would look like. So obviously get everything to one side. and it's going to look like that. Now, this is not an equation that we can easily solve because it's not a quadratic. There's no way to really factor this. And this is where in an Algebra 2 class you would kind of get stuck. However, we have the intermediate value theorem. And if you think of this as a function, the function f of x equals x cubed minus x minus 1, we can think about the y values of this function. We want to know whether this function has a y value of 0 anywhere, and we want to do this without using technology. Well, if I think about plugging some easy numbers in, if I plug in 0 for this function, I get a y value of -1. And then if I plug in 1 to this function, I get a y value of, well, 1 minus 1 is also -1. If I plug in 2 to this function, we get 2 cubed is 8, 8 minus 2 is 6, and 6 minus 1 is 5. So I'm just trying to get an idea of what's going on here. Well, look what just happened. We have a y value of -1 and a y value of 5. Now I'm looking for the x value that is going to equal 0, and 0 is in between -1 and 5. And since it's in between, we are guaranteed that somewhere between 0 and 2, there is an x value that has a y value of 0. You could set it up as a little table if you like. Imagine we have a graph. I have 0 right here on my x-axis, and I have 2 right here. And we know that we have a point at 0, -1, so there's my point, and a point at 2, and then 5. 1, 2, 3, 4, 5. So we don't know where the graph goes, but we know at some point it is going to cross the axis. And so the answer to this question is yes, and we don't know what that n value is going to be, but we know that it has to exist. If you want to practice some others, there are some practice problems in your textbook, and we'll take a look at this again in class on Monday.